We've developed two separate models that are kind of integral to the project. We've developed a model to predict craniosynostosis, and we've also developed a model to predict skin growth in response to loads. I'm Ted Vaughan, Professor in Biomedical Engineering from the University of Galway. Biological tissues are challenging to understand biomechanically because they are adaptive. So your tissues are constantly adapting to the forces around them. And that's true in craniosynostosis. When your cranium is actually growing, it's doing so because it's being mechanically stimulated by a pressure being applied to it. What we've developed is a model that can quite well predict different forms of craniosynostosis. And we've achieved that by, I suppose, better understanding the physics and the mechanics of, I suppose, each of those contributions as to whether something is mechanically driven or whether it's biologically driven. So we're able to kind of reverse engineer some of the physics that must be happening to achieve kind of the kind of final configurations that you see in craniosynostosis. So in capturing that process, we need to introduce specific growth terms in our models to be able to accommodate that increase in volume over time as you're growing as a child. At the moment, we can predict the development of the condition, and the next step is now to start to simulate the treatment and the intervention. Simulate a suturectomy where we reopen the sutures and we kind of observe how the model performs and how those sutures close again over time. And then as a next step, to bring in different device designs to compare and contrast how different devices behave compared to a kind of an existing benchmark. There's only a couple of different existing models out there, and in a lot of cases they're somewhat phenomenological in that they I suppose achieve the final outcome through kind of artificially prescribed parameters. So they don't really consider the specific physics of how that process is happening. So that's kind of our key contribution that we've been able to, I suppose, understand the mechanics a little bit better in developing the model. And hopefully we can use that to give a bit more insight to the subsequent models, because like that we're capturing the physics. So we should be able to be more predictive in how we see devices behave once we implant them in the model. What we're very interested in is to see, I suppose, the final concept designs, seeing how those devices then behave within those animal models, because that's, really good data to have alongside our modeling efforts, that we can see, are our models truly predictive, or is there more understanding needed in terms of, trying to predict how a device behaves in a particular indication like this.